This year is the 101st anniversary of this Gold Medal Award, our highest individual accolade. It's awarded to the outstanding individuals who have made and who continue to make exceptional and striking contribution to the world of structural engineering and the wider built environment. Albert is a shining example of these rare qualities due to his exceptional work. Albert joined the institution in 1984 and became a chartered member in 1987. He received his fellowship in 2008. As one of the founders of AKT Partners in 1995, Albert has pushed the boundaries of structural engineering and has a global portfolio of many prominent buildings, including the Ghana National Cathedral, Zaha Hadid's Generali Tower in Milan, the Central Bank of Iraq in Baghdad, Roger Sturck Harbour and Partners LSE Center Building, Google's new headquarters in San Francisco and London, Norman Foster's Bloomberg's European headquarters in the City of London, Seed Cathedral in Shanghai, the Vessel in New York, and many high-rise structures such as One Crown Place and 19 Elms. I'm sure you'll agree, this is a dazzling array of landmark successful projects. Each structure has been brought to life because of Albert's dedication and passion for cutting-edge technology, and he's brought into his projects throughout the UK and across the world. Albert has seamlessly merged this key emphasis on innovation and coupled it with sustainable approach to technology, whilst always maintaining a respect for heritage. And that's an impressive and commendable juggling act to achieve. I'll now hand you over to Albert for his much anticipated gold medal lecture, after which our President Matt Byatt will confer the gold medal. Thank you.
Yeah, I'd like to say good evening, and I am a little bit nervous. And I'd like to express my gratitude to all of you present here today, as well as those joining us online, friends, family, and colleagues, and clients. I was genuinely surprised, thrilled, and deeply humbled when I was informed about receiving this award. In this address, I've been asked to discuss my career and the journey thus far. I'll do my best to do so within the allocated time, but for those who know me and my passion for design, restraining myself from talking all night will indeed be a challenge. So, where should I begin? Right. My journey towards becoming a structural engineer can be traced back to my father. In the 1950s, he embarked on architectural training in the UK. However, as a black man during that era, the institution made it clear he would not be accepted. Consequently, he returned to West Africa after the Nigerian independence in 1960, with the aspiration to contribute to the development of the new emerging West African nations. He pursued a career as a surveyor. As I grew up, my father instilled a profound love of design, mathematics, and sketching, nurturing the hope that I might one day become an architect. Sorry, Dad. Fate, however, had different plans. One day, sorry, I lost my thoughts for a minute. One day, he took me to an office of an architect friend of his in Lagos. I think I was about 13 years old at the time. There I was drawn to the chief draftsman, who was diligently working on a reinforcement drawing on a large double elephant drawing board. I approached him carefully to watch and ask questions. He graciously answered all my queries and questions, explained the significance of each line on the drawing. I was captivated and in awe of his intrinsic knowledge. To me, he seemed like the most brilliant person on the planet to be able to understand every line on this huge drawing board and what they did. And that was it. I aspired to be just like him. That was my introduction to the world of structural engineering. I was born in Bethnal Green, London, East End, and spent my childhood moving between Nigeria and Sierra Leone with my parents and 3 siblings. My father's work involved establishing new local authorities in these regions. After completing a 2-year diploma in building construction in Bristol in the mid-70s, my grade paved the way for me to attend the University of Bradford, where I embarked on a degree in civil and structural engineering. Yeah, that's me with the afro. The experience was incredibly significant for me. Being the sole black student in the entire department came with considerable challenges. It was a trying period to be a young black man in an environment that, at times, posed physical risks. During my first year at university, I established the first Taekwondo club. I fell in love with this beautiful martial arts, which also provided a sense of security, allowing me to focus on my studies. I never had to use it in the university. I must give special recognition to certain tutors who provided unwavering encouragement and support. Their determination enabled me to enroll in one of the first master's course in structural engineering at Bradford. Only 2 of us finished the course. My initial employment was with a small practice in Bedford from Bradford. So it's all the B's. Subsequently, I moved to London, working for Price & Myers for Sam Price, before joining the office of Anthony Hunt, a renowned gold medalist, whose mentorship was instrumental in my engineering development. Tony Hunt taught me the power of sketching in explaining the design process. Working with him was a privilege. In 1995-96, along with Robin Adams and Hanif Kara, we established AKT. As I mentioned earlier, I was deeply honored by the citation from the institution for this award, as I believe it recognized my approach to engineering and design. Over the years, I've been involved in and I've led numerous remarkable projects. I feel an overwhelming sense of excitement and passion about being part of the process of constructing challenging and sustainable structures. From the beginning of my engineering career, I have exceptionally been prolific in my involvement in structures, while nurturing and mentoring bright young engineers. I have surrounded myself with some of the brightest engineers, I believe, in the country. In this presentation, I would like to showcase some of the projects that have shaped my perspective as an engineer. I firmly believe that every project has an element of innovation that makes it unique and valuable. Every single project. I've been fortunate to lead several high-profile schemes with my team, and this has been made possible, this had only been made possible by having the support of some great clients, some who are here today, architects and partners. Their continuous encouragement to push the boundaries of innovation has been instrumental in our journey. In the upcoming series of projects, I'll guide you through a journey of increasing research, calculated risks, innovation, and impactful outcomes. These experiences have led me to where I stand today, equipped with valuable insights. This journey has been truly transformative. It's not over yet. The first project I'm going to present, this is in a pseudo-chronological order, is the Royal Academy of Arts, Sackler Galleries at Piccadilly, when I was at Hunt's, when I was working for Tony Hunt. It was an interesting project at the time with Foster and Partners, and it was to actually infill a gap between two historical buildings and provide a new gallery space to the roof. The challenges to this project, and you've got to remember this was back in the late 80s, was there two main issues. One was the fact that the norm of trying to create a half portal or a portal structure required eaves beams. But the architecture, Norman's architecture, was to try and bring as much light into the space from the rear of the building. So his idea was to have glass that goes up and actually folds over the roof. So the challenge was to actually create a half portal without any eaves member. And back then in the day, there was a lot of negativity in doing it. But going back to the fundamentals of engineering, of what is the purpose of an eaves member, we were able to do it without having to provide any restraint. And secondly, it was to introduce one of the first glass stair in public space of this scale. Now, back then, there was hardly any glass stairs. So, had to design this glass stair without it being laminated, toughened, or heat soaked by using pure, simple anneal glass. So you could see all the eyes raising. So this was, as I said, this was going back to the fundamentals of engineering and materials. So the whole thing was done by encapsulating each thread so tightly that in a collapse situation, it will not create 3 hinges and it will stay in place. And that was then engineered that way. For me, this project is the early insertion of modernism. Each structural existing old buildings, which was a listed, I think it's a grade 1 listed building, and put a modern insertion while they both work in true harmony. The second project I'm going to present is the West India Quay footbridge. This was a competition at the time which we did with Jan Kapliki, Future Systems, back in 1996. That tells you how long ago. The brief was almost an impossible brief because you've got a tidal dock that varies up to 1 meter, and the architect said, Jan Kaplike, why don't we float it? But it's tidal and it had to be opening. The center had to open. How do you get a floating bridge in a tidal dock to open and close without clashing? So we started going through all the options, floating, pontoons, the works. And I can actually remember I was giving my eldest daughter, I think she was about a few months old at the time, giving her a bath, and we were playing dockies, pushing the dock in the water. Eureka, the moment arrived. Let's pre-stress the pontoons into the water. And that was the solution. Trying to go through the proof system back in 1994, 95 was proving very difficult. But we came up with the idea of having double pontoons, 10 meters long, 3 meters diameter, and doubling them with a cross member, and then using a cable to press them to the bed of the dock. By doing so, any tidal movement is eliminated. You only slightly feel the movement. And if any of you have been there, you'll see that's the way it works. The next challenge was then, how do we deal with the opening mechanism? And we came up with this idea of actually counterweighting it through geometry to create a very elegant solution. And it was so well balanced that you can actually push the opening of the bridge with a finger. So we end up with the tiniest hydraulic actuator, which was so small, we actually fitted it inside the tube, the spine tube that supports the bridge, to open and close the bridge. And I must say, the guy who fabricated this was Bill Toston. And for me, he was one of the best fabricators on the planet. He was an artist with metal, and I'll talk a bit about him in the future. I am trying to present projects that actually help to explain the way my mind thinks, the process I go through with engineering. This project, we actually had to go into the archives to try and find a picture of it. This is the Britannia oil rig, which is the last oil rig in the North Sea. And we were approached to do 4 staircases up to 8 levels to provide access up and down. And as you can see with oil rigs, it's all steelwork. And the issue here with so much steelwork, how do you maintain the protection on this steel in a very aggressive environment of the North Sea? So, having talked to the fabricator who came to us, he actually suggested, we were having a real workshop, and he said, what about aluminium? We said, yes, aluminium oxidized and you don't have to maintain it. How do we sell it to the main client? Because it was 4 times the cost of a steel structure. So we all trotted down to the client and we explained we're going to do it in aluminium, not really understanding the challenges we had moving forward. So he said, yes, that's great. And then only to realize that you cannot weld aluminium without reducing its strength. Except there was only one firm at the time who could do so, VW Audi. So I thought, right, let's talk to VW Audi. So somehow I managed to get hold of the chief engineer at Audi, and they've just employed a number of scientists from NASA who can then deal with welding aluminium without reducing its strength. So I can't even remember how I got to him, but I got to him on the phone. And I said, this is who we are. We'd like to do some incredible aluminium structure. We'd really like you to give us some insight as to how we can weld this aluminium, for these days. And all I heard was clunk. That was the end of the conversation. But we did manage to do the project a lot lighter, actually quite stiff for what it's supposed to do. Then the next challenge came on board, because if you're doing anything to do with the North Sea, you need to get approval by insurers, Lloyd's Register of Shipping. So they brought an army of engineers in to say, right, these are the procedures you've got to go through. We were a small practice at that time, and one of them, at the top of one of the procedures, top of the procedure is that any structure you're doing in the North Sea needs to be analyzed using finite element analysis. Back then, it was 10 to 20,000 just for the license. And our most ambitious computer in the office then was the LC3 with 64K memory. And I can remember, right, where do we go from here? The solution wasn't the FE analysis. The solution was having a conversation with the engineers, which are organized, to discuss the fundamentals of analysis and structures. So, big meeting, sat there and I said, right, guys, there are three methods of analysis. Stiffness analysis, which we had, finite difference, and then finite element. If you model a finite your stiffness analysis carefully, the difference in result to FE analysis is about 5%. And I went through all the theory with them, and they could not argue with the mathematics. And they then approved us to use a stiffness analysis to do this project. And I think it was the first. So we had to run it on a 64K Apple Mac that took 17 hours to run. But we got there. Moving on, one of the other early projects we did was the rainforest in Hanover. And this building was the precursor to the Eden project. Because when we left Anthony Hunt's office, the Eden project was in the office, and it was a glass structure. Obviously, we did this competition with a very young architect then called Ray Hall, and this started back in 1997. And there was this wonderful material called ETFE. It has a little bit of insulation because you're talking about pillows, and it actually allows UV rays through the material, which means it's actually good for plants, better than glass. But it wasn't codified back then. So we went through all the tests, German and everything. We then developed this scheme. And one of the interesting issues we had was that the structure itself is not a pure dome. And because it's not a pure dome, we had two issues when we presented this, our engineering solution in Hanover, in Germany. This was just after the wall had just come down. Was one, the struggle to accept ETFE as a structural product. And secondly, the shape of the enclosure and the dome was outside the DIN standards. And that again was not acceptable. But we were adamant, and we stuck to our guns, and there was a lot of heated arguments and palliatives. And eventually they had to get a professor from the university to actually go through all our results to then approve it, to say, yes, we'll let it happen. And immediately afterwards, one of the senior architects then sat on the panel for the Eden project and said, what are you guys doing using glass? There's this product. And the Eden project got changed from glass to ETFE. And you can see, because of it's got a little bit of insulation properties, they were able to create a super tropical environment in the space without having to lose so much heat. And we finished in 2000, and one of the South American countries used it as their exhibition space for the expo. Moving on, I'm not showing you fancy projects. I'm showing projects that has that essence of some of our thought process. This is the LSE library in Aldrich, part of the LSE, and it was a project by Foster & Partners, and they were interviewing engineers, and we were not that big back then, and this was about 1998. We were then put in as these young up-and-coming engineers, and we were there to only do the dome in the atrium for the glazing. And then we're up against some of the usual suspects. And the director of estate for the LSE then turned around and says, why are these guys put just to look at the dome? Just put them in with everybody else. When we got the brief and everything, this building used to be the headquarters for W.H. Smith. And the whole concrete building is fully carbonated. It is actually the building that was used to write the Syria guide for how to identify and deal with concrete cancer. Great. The first thing we did was to say, and the scheme was to knock down the whole internal of the building and put a new structure. And the first thing we said, we are not knocking it down. But they said it's carbonated. We said, so? If you actually understand the chemistry of concrete, carbonated concrete, it gains a tremendous amount of strength while corroding the reinforcement. So the solution we came up with was to find a retardant which we actually poured over all the slabs that coated itself around the existing steelwork to 10 times the requirement of protection. Taking a lot of dust samples, cores, we then said, keep the building. But then it wasn't strong enough. So we stripped out the old clinker concrete, because the building was built before the First World War, and we then bonded a high-strength screed. By doing so, we increased the lever arm of the slabs and reduced the stress in the bars. That way, we were able to actually add more load to the structure than its original capacity, and saving the client tons of money. But for us, it was the right thing to do. It wasn't just about knock it down, put a concrete structure. It was about retaining a bit of heritage while using modern analysis and understanding the chemistry of the materials we use and the properties. Inside the building, we created this amazing stepped ramp, which is the precursor to the Mayor of London office, again by Foster & Partners. This step ramp did not meet any regulations. It wasn't even in the building regs. So we had to build a section of it and get the building inspectors to come and run up and down it. And when we first delivered this, everybody thought it was concrete, smooth FRC or something. It's actually steelwork. This was done by Bill Tustin with what we call hidden wells. I've never seen it before. So it was a craft between engineering and fabrication. And for me, it's one of the most beautiful step ramps anywhere. That's the early AKT staff. The next project I'd like to show you is the East Beach Cafe. And this came about with Thomas Heatherwick, where he was working on it for a while, and he wanted to create this driftwood. And the client, who's probably here, decided to create something much more entertaining and iconic on Littlehampton Beach. So she bought this timber shed, got Thomas to come up with a design. Thomas came up with a design with this shell with a lot of internal columns and everything, and it wasn't going very well. So the client then said, I like Albert's view on this. So we looked at this in the office, and you could see the passion of what the client was trying to do and what the architect was trying to do, and it was very aligned. In that alignment means that what was being proposed needed unique solution. And for us, it was first taking the architect's model and remodeling it. Not only did we remodel it to make sure all the curves and the dips were done in such a way that it will not capture any moisture, it will drain off. We took all the columns out and insisted we're going to try and get this into work as a shell without any internal supports. Then we also had to think about the environmental. So, the first person I contacted was Bill Toston. As I said before, and I do believe this, he passed away a couple of years ago, almost about 3 years. To me, he was an artist with metal. And he basically said, I have a 1950s roller somewhere in the shop, and if you can do a metal to use that to do it, I'm on board. And you can only do 600 millimeters wide, and it's not more than, I can't remember, 6 millimeters thick. So we redesigned everything to strips of 600 so that it can roll it, and the whole thing was rolled with that hand metal. And then the inside, we literally sprayed it with insulation. And if you go there now and painted it, that's it, to get the environmental in place. But we had a lot of fun getting it through.
We did, Albert.
Ah! Jane! The client is sitting at the rear. The next project was again with Thomas. There was a competition for the expo in Shanghai. And I can remember we had a conversation, let's go for this. So we went for it. And we went through a lot of options. And we entered the competition, and Thomas was saying, I've got this idea. I'd like to do a box with about 20 or 30 spikes sticking out. And I said, 20 or 30? Why don't we try 10,000? He said, can we do that? I said, I wasn't sure whether we can, but I was quite prepared to give it a go. So we decided we're going to try and get 10,000 spikes into a space to create this. And by the way, this is not a CGI, this is the real thing. And the idea of this spike, which we came up with after a lot of research, was clear acrylic as a composite with aluminum sleeve. And the issue here for us, technically, was acrylic resonated at a very high frequency, which means it can resonate itself into destruction, because we had to design for typhoon issues in Shanghai. By actually bringing them together, that resonance reduces, which actually creates, there's a movie of this, creates an amazing effect. But also the clear acrylic can bring clear light through it, into the space beyond. So came up with this idea that every spike in this is exactly the same length, 7 meters. And I remember this was the idea we presented, to say prefabricated timber box, drill. We never got to 10,000, by the way. There was just enough space for 10,000. We got to 6,000. To literally punch holes through this timber. And then Thomas came up with this amazing idea to actually use seeds from the seed bank. It was called the Seed Cathedral. And as you can see, the internal, the reverse of the shape externally formed an amazing space internally. And during the day, light penetrates into that space through every single acrylic rod. And in the night, the light goes in reverse. Again, we had some challenges. And the challenges actually became a diplomatic problem, where the Chinese government at the time refused to sign off our design. And the British government was very clear that this piece of land for the expo is part of Great Britain, and we can do whatever we want. And then afterwards, we'll demolish it, and you can give it back to the Chinese. And the Chinese were saying acrylic and aluminium in our composition was not a structural material in China. So I had to take, Thomas and I had to take some very urgent flights to Shanghai to meet the ambassador's representative and a member of the Chinese government, and it became a loggerhead. This went on for a bit. Eventually, it was agreed that we get a professor from Tongji University to evaluate what we've done and approve it, which is exactly what we did. But even then, we had to compromise for political reasons. But it got built. And the brief from the client that we had to be one of 5. We have to be in the top 5, because they actually score each pavilion was part of the brief. We actually came first and won the Lubetkin. Mazda Institute. The reason I've put this project in is for one reason and one reason only. From my experience, this project actually kicked off in real detail the whole conversation of zero carbon. Because when it was built, the client literally gave us a challenge. It was an incredible challenge to try and reduce the passive heat on the building. And we had 6 weeks. We were called in and said, we interviewed engineers from everywhere, and we were interviewed, and they said, what as engineers are you going to bring to the table to deal with sustainability and zero carbon? And we said, we only got one. We said, and you got to remember again, this is back in the early 90s. We said, why is it in the Middle East back then, every time they were doing concrete of any scale, they have to use crushed ice into it to stop the cement, the hydration. We said, why don't we just take all the cement out and put a binder in and let what the sun in the Middle East does do? And they said, is this possible? And we said, yes. So we took 80% of the cement out. They had to import the binders from India. And the client was so impressed and said, 6 weeks, we want foundations to start because we're going to bring the sheikh to see what we're doing. We're starting with a very sustainable approach. And it got done. And some measurements were taken by Foster's afterwards, and you can see how the radiant temperature in Mazda is reduced compared to downtown Abu Dhabi in the hottest day. And this is relevant, very relevant, because we're using the thermal mass and the basement, or the podium we did, to cool. And from my experience, this is one of the projects where you had some of the first electric cars self-driving using magnetics. So if you go down into the podium area, you just sit in the car, you type where you want to go, and it'll take you there. And I remember one of those cost, I think it was 1.3 million at the time. Anyway, they only did a handful and then they stopped. Technology moved on. The next project I'm going to show, this is a fascinating one, this is the tallest building in Accra. And the reason I've put it on was, again, to try and explain how our office thinks. We got a call from the architect saying, "I've got this client. He's not crazy, but he wants to build the tallest tower in Accra, 25 floors plus." And he said, "Would you like to be involved?" I said, "Of course." So he came over, we had a meeting. He says, "I'd like you guys to get involved in the early days and move forward." I said, "Fine, that's fine." And I said to him, "You want to do 25 stories plus here? Have you got any piling rigs in Accra?" "Yeah, we've got 3. "Right, I need piling rig that can do 750 to a meter diameter as a minimum." He said, "I'm afraid the ones we've got can only do 450. I said, "Well, okay." Then he turned around to me and said, "Albert, do you think you can, put me in the direction where I can buy a piling rig?" And I said to him, "No, you're not going to buy a piling rig for one project." And I said, "Leave it with us." The solution was not to put a piling at all. So the first thing we said to him is, your single basement is going to be double basement. Put all your plant in there, great height, and we're going to create a caisson in concrete. And you do not going to pile this building, even though we're in a mass seismic zone, which is exactly what we did. But I'm also very proud of this project because every material was done locally. Even the block work we used a local block work of unknown strength, tested it to form the external cladding to the building. And it's still there today, and it's still the tallest building using. And one of the most beautiful things was that they didn't have tables, so it's not a flat slab. We actually went back to the old beam and column process where we actually put all the beams on the perimeter. And every single column is one width, 200, to match the local block work. And then the length depends on where it is. And all the floors were done without any table form, because they didn't have any table form. So we went to the local concrete factory that produced 100 by 100 profiled lintels for doors. And we got them to extrude them 3 meters. And they literally laid them, no craneage, laid them next to each other, sellotape, clear sellotape in between, put all the bars, run into the beams, topping concrete, and that's what made all the floors with a single line of support. And that's working with the local. This project with Zaha Hadid in Baku was very controversial at the time. She went to do this project, and I think there was a lot of people in the industry who were very critical of what she was doing back then, but her view was very clear. We're trying to do a museum and exhibition space, concert hall for the people, which is what was done. Our involvement was very much in a high seismic zone. The codes locally, and all the meetings were held in Turkey, in Istanbul, was basically to create square, solid structure. We went for a very flexible structure. So we spent a considerable amount of time analyzing it and looking at the response of the structure. This is all exaggerated. But the other thing we got involved in very quickly was we actually wrote our own software to look at the cladding approach to the building. because the architect was very clear. She wanted the pavement to literally wrap the building and the same material. So what we did was we wrote this software and gave it to the architect and said, right, play with it. Increase it, squeeze it, create the parameters, and it nested the whole thing to give you the percentage of standard flat elements, curve elements, and special. And when we finished, so we went through different scenarios, and you can look at the risk profile of all the specials. And this was plugged into the fabrication system for the cladding. And this is the end product. Also, politically, we could not even find any fabricator in the world who wanted to go to Baku to build it, apart from Mira. So a lot of redesign was done to make that happen. Getting close to the end of the projects I'm presenting. The next one is, this is one I'm very passionate about. This is the South Bank Tower in Southwark. And this project was a call from one of my best clients, he's sitting just there, George Kiriakou. He said, we're looking at this tower, it's pretty derelict. It hasn't been used for a long time. It was a hotel for the pigeons in South London. And the due diligence says we can add 4 stories to this 30-story tower that was built in the mid-70s. And there was also a planning consent to demolish everything and put about 5 domes on it. And he said, what can we do with it? So obviously we all went round, looked at it, and I can remember I said, I'm sure we can get about 8. And then came back, the numbers was done, he said, can we do a bit more? I said, give us some time. And we then decided we can put between 11 and 13 floors on the building, on the existing building. But this was done without strengthening one single member of the original structure. And even up till today, people are asking me, how did you do that? The way we did it was that we changed the load path of the structure. Not only that, we used a modern method of analysis for the wind. We actually wrote our own CFD analysis for wind before any other consultant I'm aware of in our industry, in-house. And then we analyze the wind from the wind criteria from the 70s and for present day. And we have better data now around London. We also took a lot of samples of the concrete and we could see it gain a huge amount of strength because all the external columns are precast. So they were all done to very high quality. We had 2 tube lines running underneath the building, under impals, which were now under overly consolidated clay. By doing that and changing the load path, we actually took the original core and tore it apart. We didn't demolish it, we took the internal out and reconfigured it, and we end up with a slightly stiffer core. By changing that load path, we were able to take that building and make it into that building, a much elegant tower. So rather than demolishing it, we said no. And I can remember, I was one of the planning review panel in Southwark at the time, so I had to excuse myself. And one of the objectives was Westminster across the river, because they thought it was a joke, an April Fool joke. So I had to go present to say, it's not a joke, it's real. But as I say, you cannot do these projects without having very good clients who really are there to support the approaches. I'm going to run through this very quickly. Everybody knows about this project, and the thing I'm going to say about this project was a whole block and with Bloomberg headquarters, and again with Foston Partners, and again we ran into the usual. And one of the challenges of this project was the fact that on the site we had 3,000 existing piles, the existing building which was demolished. And there was a guide that was produced on how you test and reuse existing parts. You have to take a sample of them and test them. So all the gray bits in the piling thing are all the existing parts, and the pink bits are the new ones. So, and I can remember there was a whole conversation about the serial guide to do this and everything. And it was going to cost thousands to test a percentage of these parts. And we had some very, very heated arguments, and I just said, it's not going to happen. It's going to cost the client hundreds of thousands to do that process. So we said, we're not going to go through that process. What we're going to do is detach. Again, this is all driven by insurance companies. And I kept thinking to myself, hang on, we are the engineers. We should be telling the insurance people what the risks are and what the positives are. We cannot be designing to insurance companies. So we then said our solution is to detach all the piles, because you're not allowed to put a new building on old foundations, and then put a raft on it. And philosophically, our approach is the existing piles are part of the ground, the substrata, and they're there to strengthen the ground. I'm going to put a raft. By detaching it and putting a meter of crushed material, the stresses goes into the soil, but then goes back to the same piles without having to test the piles. So by doing a series of very intricate analysis, we're able to prove our point. But that wasn't enough. All the big geotechnical departments in London were brought into this. And the client, it became a big issue where the client had to get Ewan Cantor from Cantor Sinak, who did most of the towers in New York, out of retirement, to come review our approach and the standard approach. You can guess, we delivered the project. I'm almost at the end of this section of my address. The vessel, to me, is a very controversial project. The client wanted a sculpture where people can do this in the west side of New York, on a podium that covers the rail tracks and very huge frequency issues. Wanted a sculpture where people can go, a symbol to the center of the development. And this was bar-related. So we flew to New York, they came to London, and Thomas decided he wanted something more. Rather than a sculpture that people can just stand and take photos, something that can be used. So he came up with this idea. But the issue was the criteria was enormous, because they were going to use it for everything, from concerts, people use it in the morning for exercising. The ambition for the project was a very good ambition. Sadly, it hasn't gone that well. But from a structural point of view, it's all to do with dynamics. And that dynamics and a huge amount of analysis was done. But for us to make this work, every aspect of this design, of the architectural form, is a structural form. There's no cladding, secondary cladding to this. We had to use every single element as part of the structure. And we had to run a huge amount of analysis to make it work. And then we had to get Chimolai from Italy to fabricate it, because the Americans were struggling to fabricate it. So for us, and we had to put some dampers in so that it can hold concerts, it can run up and down, and we even had a curved lift internally so you can bring people to certain parts of the structure. So the last few slides I'm going to go through, the Google headquarters in San Francisco, in North Bay Shore. We were sort of put on a plane over there to talk about both a master plan and creating some biodomes. The client wanted enclosures with hospital quality air for his staff. So a series of biodomes was designed. And this was done, it was a collaboration between Biaki Ingalls and Thomas Heatherwick. So we spent a lot of time there. We looked at glass and ETFE. It was clear we're in a very high seismic location in North Bayview. But the issue of being in a high seismic, you have to also look at what's below ground. And the substrata on the side is silt and sand, highly waterlogged. So in a seismic situation, the whole thing just liquefies. So our starting point was that we have to have a foundation system that floats, because trying to pile it meant that you'd have had to go to Australia with your pile, and that wasn't physically possible. So the solution that was developed was to use a cable net, a cable structure. Now I have a real problem with cable structures. They're very light, they look beautiful, but all they do is transfer the forces and the stiffness elsewhere. You end up with tremendous amount of tension forces to create that form and that shape. What that meant was the amount of concrete you would have had to put in the foundation system to hold this cable net with a glazed enclosure. We could have built an airport with it. So it was definitely not a solution. So what we came up with, it was what we call a grid net. The grid net was by using flats, overlapping flats, to form the same shape. What this does is put stiffness back into the roof structure while maintaining the form and reducing the amount of tension forces around the perimeter, which means you can do a nice floating raft foundation, which is exactly what we presented. This is what we presented to the client to try and explain this. In a seismic situation, you had a cable net and a grid net, and you can see one of them it's not converging fast enough. This is the final structure. And you can see how light and airy it is internally. And this project then led to the Google in London. We've done some amazing stuff in this building, but I can't tell you. There's so many NDAs on this. But what I can say is that it's probably got one of the largest timber CLT floors in London. And every fourth floor is a concrete floor, which allows us to deal with the fire situation in a compartment. And all the external is done in timber mullions. But I'm sure there'll be lots and lots of conversation about this building when it's opened, still on site. The external of the building, there's no external columns. The whole thing is floating. It's 300 meters long, 22 meters wide on one side to about 65 on the other, and it's a public park right on the top 10 to 12 floors. The last two projects I'd like to present, one of this is the Ghana National Cathedral. And the challenges with this project was, yes, went right up to the cabinet. The whole idea was in Ghana was to create a center for Accra, for the capital, where you have a multi-faith cathedral, but also you have an exhibition hall, a library, and a crypt, and also for it to be a center for national occasions. And this cathedral was built to have 5,000 people internally, and when you open the two ends, you can have an extra 5,000, a total of 15,000. So the span is about 85 meters, and the length is about 230. And the challenges we had here was the design was to go from a sort of catenary form into a castellated form, which represents some of the kente covering from old traditionally. And the major brief for this was we had to use local materials all the way through. So for me, this project aimed to achieve a seamless, impossible reverse engineering of a complex state-of-the-art in a developing environment. Part of the brief was also a goal to share knowledge with the engineers and empower the local industry and provide them with confidence that, yeah, we can do a project of this kind. And my team in London have been amazing. Finally, I thought I should show the Hilo building. And the Hilo for us was the next generation after the South Bank Tower. And the client that called me to come look at this is also sitting here. And basically, it's a 17-story exchange building. And we went to look at it, and he said, oh, some engineers have said they could put this much on it. Can you do better? A challenge. So, and a challenge it was. So the blue purple bit is the original building. So what we had to do was strip the building down. We had two major cores internally. We had demolished one of the cores, expand the girth of the building, and then we added 13 floors to the existing 17. And we also did this without touching the foundations. We had to augment the foundations with extra parts because we made the building wider and put a lightweight structure. And the columns at the top of the existing we found were not strong enough, so we just put steel casings on them. And actually the client, as part of the interiors, just left them like that. It's part of the architecture. So in a way, this slide shows you the transformation. The white building is the original building. The one in the middle is the whole thing stripped right down with the core, one of the core removed. And obviously on the right is the end product. And I must say the architect was fantastic. And the cladding system, to me, is one of the best I've seen anywhere. So, oops. Steve Toon. Right, this comes to the end of this section of my address because I hope I've been able to share with you the thought process of the way I think as an engineer and my team, AKT, as a practice, and most of them, a fair amount of them are here today, the way we think as an organization and the way we look at structure. We don't just look at it to just solve the problem. On some of our projects, we actually challenge the brief and we challenge the client. But for us, the project is the key. We will protect a project to any cost. Now, going back to my written form, these are the few projects I've had the privilege of leading with my team. And as the lead design partner, AKT, and overseer of majority of the international projects, I would like to take this opportunity to address some of the issues that, in my opinion, warrant consideration within the engineering community. I take great pride in my role with AKT. I have consistently strived to foster diversity and inclusivity within the organization and beyond. This commitment extends beyond the quality of just our design. It is a fundamental aspect of our positive business approach. apologies. Yes. It embraces and enhances the energy and the perspective of various groups and cultures. We enrich our work and contribution and to a more inclusive environment. I would also like to raise that during my extensive travels to numerous countries, I've been struck by the remarkable structural designs, but seemingly out of context. We are fortunate to train some of the world's finest structural engineers. To further enhance our capabilities, it is imperative that we become more attuned to the culture and traditions and the aspects of the regions where we provide our services. While we have developed exceptional designs that excel in European and American context, they often do not translate well to areas such as the Middle East, Africa, and other parts of the globe. As engineers, it is incumbent upon us to acknowledge and study the local traditional construction methods and materials. By doing so, we can gain invaluable insight, especially in the context of sustainability. The question then arises, why can't these methods be standardized and codified? We have to make the effort. Also, our world is confronted with an immense crisis of global warming, and it's not something we can ignore. As designers and engineers, we find ourselves on the front line, tasked with crafting solutions to these pressing issues. To make a meaningful impact, we must return to the fundamental engineering principles, drawing upon our expertise and knowledge to contribute on a massive scale. This entails a reconnection with the core tenets of design. Also, as structural engineers, we are well versed in the philosophy of collapse theory, which underpins the contemporary design approach. Our focus should shift from merely conforming to building codes to a far more proactive stance, designing structures capable of withstanding the current and future external forces we face. This should be the case instead of allowing codes to dictate our designs. We should proactively craft good design and then use the regulations and the codes to ensure we meet safety, functionality, and fit for purpose. Code constraints should not limit the quality of our design and the selection of materials. Numerous structural materials exist in our field. Yet, many engineers limit themselves to a handful of narrow selections throughout their careers. To tackle the complex challenges posed by global warming, we must broaden our horizon and explore the full spectrum of available materials and processes. Timber, while valuable, is not the sole solution or panacea to the embodied carbon problem. All materials and processes have a place in combating the carbon emissions. Composite materials, for instance, can be tailored to provide the necessary components to counter some of these external forces. True innovation may not necessarily involve creating iconic structures, but rather combining elements and materials ingeniously to develop suitable system for specific purposes. Pardon me. It is disheartening when excessive attention is given to reducing minute amounts of embodied carbon just to meet standards. Reducing carbon in our structural and building system should be an inherent part of our design process, not a post-calculation of what we've done. We have other demanding criteria to grapple with. Lastly, I'd like to address an issue which I believe is hindering the development of our design industry. We must unite our efforts to inspire young people to join the built environment profession. Each firm I'm aware of have its own approach, but the effectiveness varies considerably. Instead of blaming the government and institutions, we should pool our resources and collaborate with organizations already excelling in mentoring and supporting young people. Like a program such as the Open City Stewardship, a program which I strongly endorse. They encourage young individuals from diverse backgrounds to pursue careers in architecture, engineering, surveying, and design. And they actually do this with students from primary school right through to university. As an organization, they exist on public donation while providing access to our most finest infrastructure and buildings, allowing the public to appreciate the physical beauty of what we do in our industry, not just looking through pretty pictures in magazines or social media. Finally, being one of the first or one of the few black structural engineers of my generation has at times presented very tough challenges. Some of these challenges have come from unexpected places. However, I've also enjoyed an enormous amount of support from many people. It's a fantastic profession I've really enjoyed, and I'm still enjoying it. I'm passionate working along some of the many talented and creative individuals. A lot of them are AKT and others in the industry. I'd like to finish to say I'm very grateful to my wife Debbie for her continuous support from the very early days we met, dealing with all the ups and the downs and the issue of designing till odd hours in the night. And I'd also like to sort of thank my whole family for their continuous support. I'd like to end by thanking the institution for this day. Thank you very much.
What a fantastic, insightful and inspirational lecture. And I, for one, am really glad that you didn't make it as an architect. I was really heartened, actually, by one of the keys of your presentation, which kept coming back, and that is nurturing, mentoring, and developing those around you, and effectively giving back. And I think that is so important and so brilliant. It was also fantastic that you've still got this curiosity, this always curious, track down the knowledge, even if it means trying to find someone in Audi. You know, genuinely push for the right solution, reuse and extend existing structures rather than knocking them down. new materials, novel use of materials, buildability. How many times do we all need to rethink about that? And fundamentally, coming back to good engineering principles. That was such an inspirational presentation. What a career, and thank goodness it's still going strong. I would like to now actually present you with your gold medal, and then we'll open up the floor for questions. So I'll present the gold medal, then if you could join me here and we'll open up for questions.
Thank you.
This is our highest medal, our highest achievement to any individual, and it's totally deserved. Well done. Thank you very much.
Just you. I'd like to know if there's anything you wouldn't try in engineering, Albert.
I must say, as an engineer, I made it very clear at the beginning of my career, I will not get involved in any project that's got to do with the military.
I meant structural challenges rather than ethical challenges. But I do appreciate that.
Structural challenges, no. I'm quite prepared, and I do believe, and I like to think the organization I represent, we've got enough talented people to have a go at pretty much any kind of structure.
I did see a raised hand at the end, but so while you're walking down there, I've got a question online, which unfortunately the attendee didn't put their name, but it says, any advice for young engineers to build their practice in a way that they can look back and be proud of?
Oh, this is a very simple one. Keep learning. Seriously, I mean, I'm in my early 60s and I'm still learning. I'm learning from different aspects of the industry, and you're bringing that into what you do. You got to keep learning, you got to keep an open mind. For me, that is fundamental, and that would be the advice I'll give them.
Thank you very much.
Hi, I wondered, the building that you put on the caissons, the 25-storey tower,
Yes.
has that been tested yet? Has it faced any seismic action
yes,
yet?
it has. It has.
And how did it perform?
Yes. Well, it's still there.
It's still there.
People are still living in it. So, yes, it has been tested, yes.
Hi, Tim Burton from SH Structures. Albert, if you could change one thing that constantly frustrates you, project after project, what would it be?
Oh, how much time have we got? I mean, we're in an industry where you're constantly being frustrated. And the intensity of the frustration depends on the context you're dealing with. My present frustration are insurance companies. I mean, we went through a period where we were designing to agent loads that was totally outside the code we were designing. We as the engineers determined what the load criteria is for various typology of spaces and buildings, and yet we had agents telling us to design to almost double that, and we all carried on doing that for years. And I sort of believe that right now we're being dictated to by insurance companies when we're the engineers who should be telling them where the risk is and what the issues are. But we find ourselves it being done in reverse. So yes, I can go on and on.
Give us a practical advice about the thermal analysis of RC buildings. Yeah, apologies. I probably should have read that in advance.
I'll have to think about that one.
Yeah, okay.
The appropriate answer for it. But actually, it's not such a silly question as it sounds. I think we do have some very sophisticated analytical processes now, which we can use to actually deal with not just the thermal, but also movement. We can actually analyze as the concrete is curing. So it's not, it's quite a good advice. I would say, as I said before, you can get very good computational methods and very good feedback approaches to help you do that. They're out there, other industries use it for other materials, for various materials. So there's no reason why we can't use it in the engineering. On some of our buildings, like the South Bank Tower, we end up putting monitors and stuff on it. And we actually been monitoring the building now for, I can't remember, someone in the audience will tell me, we've been doing it for years. So yes, it is possible.
If I'm allowed to ask a question as an architect, Robin Nicholson, you showed us the tower in Accra, but I know you're involved in the African Futures Institute. Could you tell us something about what that might, where that might lead?
Very good question. Yes, I think I'm a trustee of the African Institute, and the whole issue with the African Institute is that we need to provide architectural schools. We need to provide environment where we can get the African professionals, create African professionals who are working in the context of where they live. It's no argument, we cannot have an argument that British architects do some of the best buildings in Britain, right? We need African architects, African engineers, African surveyors to actually understand that they have actually got the ability and the exposure to create their own form and their own architecture and engineering. So the Institute is there more to expose the profession to what's happening internationally as a conduit for them to understand how things work and what's happening internationally. And eventually to actually create a learning venue, a teaching venue for local students from different backgrounds.
So what I would like to do is just once again thank everyone for their enthusiastic questions, and thank you for your really insightful and considered answers, and addressing them so eloquently. Now, before we conclude, I know we've given Albert a round of applause, but if we can please once again just show our gratitude for such a fantastic, inspirational talk. And once again, congratulations, Albert, on being our 2023 gold medalist.